Okay, so here's an example to kind of delineate what I just said about horizontal compression and stretching and vertical shifting, that relationship there. So what we're going to do is sketch both of these graphs here. Okay, so let's do the ln one first. That seems relatively easier. Okay, so x and y, let's see, 1, 2, 1, 2, 3, 4, 1, 2, 3. Okay, so ln, so for any kind of logarithm that doesn't have any horizontal or vertical shifting, such as this one, it's going to cross through the x-axis at 1, so 1 comma 0. Okay, and then it's also going to have, because we actually have a base of e, right? So ln of x is the same thing as saying log base e of x, but we just never use this notation here. But anyways, that's the same thing what it's saying. So when we have a base, so this is kind of a general rule. So when we have a base, so let's say base b, then when our x is equal to b, when x equals b, okay, or whenever the inside is equal to b, okay, so I'll actually write that instead. When input, or this thing inside, so, okay, I'm going to do a rephrasing of that here. When inside, so anything inside pure parentheses, which might be a little bit more complicated than x itself, okay, so when the inside is equal to b, then the output, then the function value is equal to a 1, okay? And what do I mean by that? That just means like when we have f of, let's say, b is equal to log base b of something inside, some formula, right? Then when the inside is equal to b, we just have log base b of b, which is automatically equal to 1. Okay, so in saying this, I mean that, okay, so right now we're dealing with a base of e, so when x is equal to e, so when x equals e, then the function value, f of e, should equal a 1. Okay, and what is e? That's about 2.71, it's just a constant. So 2.71 is around here, so we're just going to go up 1, and that is automatically a point on our graph. Okay, and with these 2 points and knowing what we know about logarithms, we can kind of just graph that kind of right away there. Okay, so it looks a little bit like a boomerang kind of thing. Alrighty, so now let's graph g of x. Okay, so all this is saying is that we have ln of x plus 2. So because the plus 2 is outside, that just means we have a vertical shifting up by 2. So we're just going to shift each of these points up by 2 and shift up by 2. So now we just have a graph that looks like this. Okay, so let me label those there. So this is our g of x, and this one here is our f of x. Alrighty? Okay, so we went over vertical shifting, which is the same thing as horizontally scaling, compressing or stretching, right? So now our job is to go over horizontal shifting, okay? So this one, fortunately, this is quite normal. So I'll just write quite normal because it is still like backwards like it normally is, in the sense that let's say we have log of x minus h, okay? So we actually have shifting by h, okay? So we have a horizontal shifting by h, alrighty? So let's do an example of this just to see what it looks like. Alrighty, so for this example, we're going to graph this function, ln of x plus 2. So inside here, we can rewrite this as x minus a minus 2. So this minus 2 is our h, right? So h equals minus 2, so that means we're going to be shifting 2 units left, okay? Shifting the whole entire graph, all right? So we have a horizontal shifting going on. So let's write our original graph. So like ln of x is just the following. So that's going to be, let me just graph the points here. So we have something that looks like this for ln of x, the normal one, and our vertical asymptote is at 0, right? And then if we move all of these points left by 2, this 1 comma 0 is going to move to negative 1 comma 0. This 2.71, or like e comma 1, is going to move to e minus 2 comma 1, so somewhere right here. You just move everything to the left by 2. And then also our vertical asymptote travels to the left 2 as well. So now our vertical asymptote is at x is equal to a negative 2 instead of where it was at x equals 0. Okay, so now to draw a graph, we just draw it straight through there. Okay, and that second graph that I just drew is going to be our f of x, the one horizontally shifted to the left by 2 units. Okay, so now let me write the general form of a transformed log function, okay? Because we've been kind of doing pieces here and there, but haven't quite gotten the whole thing. So general form of a transformed log function looks like this. F of x is equal to a times log of x minus b, and then plus a k. Alrighty, so this doesn't look too bad. We just have, instead of like x squared or something, we just have this log thing here instead, because we're dealing with a log function. So the a, b, and k are all constants. Okay, the k tells us the vertical shift, and as well as the horizontal scaling. And by scaling, I just mean compression or stretching. Okay, the b tells us the horizontal shift, which we just saw, horizontal shifting, which also tells us x equals b is the vertical asymptote. Okay, so that's an important point to make. X is just x, that's just our variable, right? And then the a in front tells us our vertical scaling, vertical compression or stretching. I'll just write here. So compression or stretching. So this is the thing that accounts because for using the common log here, or the common base of 10. This thing here could have like a different log in it, but that will be a constant as well, like I showed in the very beginning. Okay, so if we're actually vertically reflected, we're going to have a negative sign all the way in the front here. Okay, so I'll just write a little note to the side. If a is negative, or if there's a negative sign in front of your log, then we have vertical reflection. Okay, and if we have a horizontal reflection, then we have a completely, well, not a completely different looking, but if we have horizontal reflection, this is what the formula looks like now. Then we'll have f of x is equal to a times log base b, or sorry, not b, whoa, where was that? Okay, log base 10, or the common log, and then negative times x minus b. Okay, and then plus k. So then we're just the horizontal reflection is just adding this negative sign in here in front of the whole x minus b quantity there. Okay? Alrighty, so for this example, we're going to find an equation for the logarithmic function graphed below. So we're given a graph here, and it's logarithmic, and we can see that there is a vertical asymptote at x is equal to negative 2. Let me label the axes here. So x, and let's say this is f of x. Okay, or just y. We'll just call it y for now. Okay, so we have a vertical asymptote at x is equal to negative 2. So this is kind of like our b in our formula before, right? So our general formula, and we can see also that this logarithmic function is actually flipped vertically, right? So it's vertically reflected because normally a logarithmic function looks like that, but this one is upside down. So we're going to say that this is vertically reflected. So that means we have to have a negative sign all the way in front of our log, okay? So we're going to have something of this form. F of x is equal to negative a times log of x minus b, okay? And then plus some k, alrighty? And we know b already, right? Because that's a negative 2, which we obtained from finding our vertical asymptote there. So we could say, okay, so now we can add to our information. So this is negative a log of x minus a minus 2 turns into a plus 2, and then plus k. Alrighty, so now where do we go from here? How do we figure out a and how do we figure out k? So the thing is, what we want to do now is just plug in a point that we can find on our graph into this function here, and then solve for a and k. Alright, so we see that one of the points is right here. How about negative 1, comma 1? So we have negative 1, comma 1. Let's plug that in. So 1 is our y, and that is equal to negative a times log of negative 1, that's our x, plus 2, plus k. So this thing in here, negative 1 plus 2 is a positive 1, and log of positive 1 is always going to be 0, okay? So we get that k is equal to 1. So now we've obtained more information we can add to our formula. So now we know this is a plus 1. So let's continue on the next slide. Alrighty, so now we have reduced this problem to figuring out a. Alrighty, and again, we're just going to pick a point on our graph and then plug it in and see if we can figure out that a. Alright, so let's say this one, 2, negative 1. 2, negative 1. So this is our x and this is our y. Alrighty, so now we have negative 1 is equal to a negative a times log of 2 plus 2, and then plus a 1. Okay? And then if we just subtract this 1 over, subtract a 1 on both sides, now we get negative a times log of 4 is equal to a negative 2. We can divide by a negative 1 on both sides, so those both turn positive, and we can divide by log of 4 on both sides, so we get 2 over log of 4, and that is equal to a, and that's our constant there. Okay, so now let's just plug that in, so we get f of x is equal to negative 2 over log of 4, okay, and then times log of x plus 2, and then plus a 1. So this is technically, this will suffice for the formula for the function that our graph represents. Also, we can do a couple of different things and manipulate stuff around in order to get something that looks a little bit more pleasant. So let me do that on the last slide. So we have right now f of x is equal to negative 2 over log of 4, okay, and then times log of x plus 2, and then plus this 1 over here. All right, so let me rewrite this in another way. So this is actually log of x plus 2 with a base 10, right? That's the common log. And then log of 4 with that same base. So we can take our change of base formula and go back the other way. So this is actually going to give us negative 2 times log base 4 of x plus 2, and then plus a 1. Okay, so see here how we've obtained a formula which actually shows us that the graph that we were seeing, the one that looked like this, that is the graph of a log with a base other than the common log and other than the natural log, right? So it could be represented as having a base of 4, or it could also be represented as having a base of 10. Okay? Alright, so that concludes our concepts video on graphs of logarithmic functions. I hope that helps, and I'll talk to you in the practice problems video if you watch.